will announce our speaker. Our speaker for today is Konstantin Druzhkov, and he will speak about, you see the title, about invariant reductions of PDEs. Kostya, please begin. You are welcome.
Oh, thank you. So, first of all, thank you for having me. Thank you for the opportunity to discuss my results. And one of my goals today is to understand whether these results are well known or not, or at least known in some sense. Yes, and I'll tell you about our results on some reduction mechanism for PDEs, for conservation laws mostly. And this is a joint work with Alexei Shirikov. And yes, let's begin. So let's discuss the main idea. If you have a system of partial differential equations and its evolutionary symmetry of the form, let's denote it by X, then there is a mechanism of reduction of invariant conservation laws that are invariant with respect to this symmetry. And the mechanism is based on the following formula. If we have a representative of an invariant conservation law, then the lead derivative with respect to X of this representative must be a representative of the trivial conservation law. That is, on the right hand side, we must have something horizontally exact, some horizontally exact form, but on the corresponding invariant solutions, or on the manifold describing the corresponding invariant solutions, the evolutionary symmetry vanishes. It means that the left-hand side of this formula vanishes on invariant solutions. Then we get some horizontally closed element, some horizontally closed quantity on the corresponding system describing invariant solutions. And in the case of 1 + 1 systems, the resulting reduction, the result of the reduction is a constant of invariant motion. That is, it's an analog of first integral of ODE for ODEs. Yeah, and the mechanism working for any local symmetries, for point symmetries, contact symmetries, higher symmetries. You can see that this mechanism is based on nothing, roughly speaking. It's very simple. And one of my goals today is to explain that the mechanism is extremely simple. And this is the reason why I'm not sure if this mechanism is known one way or another. Maybe it's known, it is known not in its full generality, but in some cases, at least. So I would like to understand. If you have such information, please share it with me. Yeah, and another result is two computational algorithms for 1 + 1 systems of evolution equations. This is the reason why we consider 1 + 1 systems of evolution equations in this talk, because in this case, it's easy to formulate the corresponding computational algorithm, or more precisely, two algorithms describing the reduction process. This is like the simplest case in this sense. Okay, so let's begin with systems of evolution equations. Let's consider a 1 + 1 system of evolution equations having form 1. Here, t and x are independent variables, u1, etc., um are dependent variables. We can consider the corresponding projection, the corresponding bundle. Let's consider just trivial bundle, the projection onto the second factor. And this projection leads to the corresponding infinite jets. Then we consider this system, roughly speaking, we consider it locally, but of course, the generalization of these results to the case of global geometry is straightforward. So it's very clear what to do if we have non-trivial and non-trivial bundles, something like that. It will be clear, at least, I hope. Yes, so we get the corresponding infinite jets. And on the right-hand side, we have some functions of independent variables, dependent variables, and a finite number of derivatives with respect to x only. So it's just a system of evolution equations. Let's denote by epsilon the system with all its differential consequences. This is the infinite prolongation of our system 1. Or in other words, this is the set of formal solutions of system 1. We can say that points of epsilon are formal solution, that is Taylor series satisfying the system epsilon. Yes, and let's discuss the structure of this infinite prolongation. Denote by f of pi the algebra of smooth functions of a finite number of variables given by the formula 3, all possible variables on the infinite GX, and let f of epsilon denote the restriction of this algebra to the equation epsilon, to the infinitely prolonged equation epsilon. One can interpret the variables tx, ui, and x derivatives as coordinates on epsilon. Then we have the inclusion of algebras given formula 5. So we can say that f of epsilon is a subalgebra of f of pi. And the total derivative with respect to x preserves this subalgebra. So we can restrict total derivative to epsilon, or we can just use total derivative with respect to epsilon without any restrictions, in the sense that it acts on this subalgebra. And let's introduce the restriction of total derivative with respect to t to the corresponding infinitely prolonged system. Now there's have form 6 or form 7 in more compact form. Total derivative with respect to t doesn't preserve the subalgebra, so we restrict this total derivative to the subalgebra to the equation, to the corresponding equation. This total derivative with overline denotes the restriction of total derivative with respect to t to the system epsilon. Yeah, okay. And let's introduce some other notation. Denote by couple of pi the corresponding product of m versions of algebra of pi. And by couple of epsilon, we denote similar product, but given in terms of the algebras of functions on the equation manifold. And for any vector function being element this couple of epsilon, there exists the corresponding evolutionary vector field. We consider this evolutionary vector field on GX. It is given by formula 9, but one can see that this vector field also preserves this subalgebra, so we can restrict this vector field on our equation manifold, or we can use its version given by formula 9 as well, because it preserves the corresponding subalgebra. Yes, and an evolutionary symmetry of epsilon is an evolutionary vector field such that its characteristic, this vector function p, is an element of this product couple of epsilon, and formula 10 fold. That is the derivative with respect to this evolutionary symmetry of our equations on the equation manifold. Okay, and it's worth mentioning that point symmetries can be described in terms of evolutionary symmetries as well. Point symmetries and contact symmetries, they are just particular cases of evolutionary symmetries in some sense. So if we deal with evolutionary symmetries, and if we describe something for evolutionary symmetries, for arbitrary evolutionary symmetries, then we describe it for any local symmetries, including point symmetries and contact symmetries. This is what I'm trying to say. Okay, let's discuss invariant solutions now. If X is an evolutionary symmetry of epsilon, the corresponding X invariant solutions are described by system 11. This system consists of the original equations, plus we take the characteristic of the evolutionary vector field, the evolutionary symmetry, and consider the equation of the form characteristic equals to 0. Let's denote by epsilon x the infinite prolongation of system 11, that is system 11 taken with all its differential consequences. One can see that epsilon x is a system of epsilon. For this reason, we have some reduction mechanism, of course, because we have this inclusion. We have two systems of differential equations, we have the corresponding inclusion, and using this inclusion, we can take spectral sequence of equation epsilon and pull it back epsilon x, it can be considered a reduction mechanism itself, but this reduction mechanism is not the most interesting one in this situation. I'm going to tell you about the reduction mechanism, and the reduction mechanism is based on the following observation. Let us know that the symmetry x vanishes on epsilon x. Indeed, all its components are just components of the characteristic or total derivatives of the components of this characteristic. And it's easy to see that the symmetry, each component of the symmetry x vanishes on the system epsilon x. So we are going to use this observation, and to propose another reduction mechanism, not based on the inclusion itself, but based on the fact that this symmetry vanishes on epsilon x. Yes, and since we consider characteristics lying or belonging to the set or to the module cup of epsilon, the system 13 describes initial conditions that are satisfied by the corresponding X invariant solutions. Okay, what can we do in order to solve the system epsilon x describing invariant solutions in some case? It makes sense to try to use X invariant structures on the original equation to reduce them somehow. And it's true that the system epsilon x inherits X invariant structures from the original system. The most interesting structure apparently is a conservation law. So let's describe the reduction of conservation laws. Maybe we can use them in order to solve the corresponding system of epsilon x, or in order to get some essential information about the solutions of the system itself. Yes. So let's discuss conservation laws of the original system. Consider a relation having form 14. On the left-hand side, we have some, let's say, physical quantity having density P1, and we consider total quantity on some segment, x1, x2, and we consider its how it changes over time. We compare its values in two different time moments, T1 and T2. And we have a conservation law if we have the following relation. If we can say this total quantity changes over time only due to some boundary influx. So we have some other quantity P2, or density of some other quantity P2. We integrate this quantity over time and consider the corresponding values on the boundary. X1 and X2 are just boundary points. We consider how it changes in terms of these boundary points. And we have a conservation law. If we have the relation, a relation of the form 14, that is a relation that tells us that there is no source of this quantity having density P1 on the segment X1, X2, and this total quantity can change over time only due to boundary influx of something else. So this relation must hold on every smooth solution of epsilon for any rectangle phi that lies in its domain. Here we can, without loss of generality, we say that phi P1 and P2 are functions on our equation. Or equivalently, we can rewrite relation 14 in the form 15. That is, we just apply Stokes' theorem here. In this case, we say that the differential form P1 dx plus P2 dt determines a conservation law. If for some function the formula 16 holds, we say that the conservation law is trivial because in this case the relation 14 takes the form 17. Geometrically, it's clear that conservation laws form are trivial, but I would say that it's less trivial from physical point of view. When we consider conservation laws on GDEs, not on equation manifolds, then they can be considered restrictions. They restrict the set of solutions. And we describe solutions for our system. We can describe some solutions for our system using that. So trivial conservation laws on GDEs do not restrict them. But trivial of the form 17, but there are trivial conservation laws of a different type, and they can be encoded by formula 17 on the equation manifold. But I would say that its physical sense is not that clear to me. The fact that it's a non-restrictive condition, but we call conservation laws of this form trivial. From mathematical point of view, it's clear. So let's define horizontal forms on epsilon as differential forms generated by dt and dx. For instance, if p1 and p2 are functions on epsilon, then omega given by formula 18, the horizontal one form, because it's generated by dx and dt only. Besides, we have the horizontal differential given by formula 19. The horizontal differential acts on horizontal forms and gives rise to the corresponding complex given by formula 20. All differentials here are horizontal differentials. And we can define conservation laws of epsilon as elements of the first cohomology group of this complex. So they are horizontal one forms that are closed, horizontally closed, but we consider them modular exact horizontal one forms, the horizontal differentials of functions. This is how we define conservation laws, and let's discuss their reduction. The mechanism is extremely simple, I would say. Let me describe it in detail. Let x be a series of epsilon, and let omega represent its conservation law. That is, we have formula 21, the horizontal differential of omega equals to 0. So here everything happens on the system epsilon, right? We have this differential form on the system epsilon, horizontal one form. And it's easy to describe invariant conservation laws. The conservation law is x invariant if the lead derivative, given by formula 22, represents the conservation law. In this case, there is a function theta such that formula 23 holds. And this is an observation in terms of our talk, today's talk, because this formula is the reduction mechanism. We know that x vanishes on the system describing x invariant solutions. That is, left-hand side vanishes on this system. And if we restrict our formula 23 to the system, we get the relation of the horizontal differential of something equals to 0. That is, we get a representative of another cohomology element that belongs to the system epsilon x in this case. So this formula 23 is the most important formula of my talk. This formula is the reduction mechanism itself. The main observation is extremely simple. It's not that easy to turn it into a theorem, actually, in this case, because the observation itself is extremely simple, almost trivial. Like we observe almost nothing. Just one formula, and this formula explains itself or proves itself in no time. And our reduction mechanism is based on this formula 23. And you can see that actually in this case, it's not that important if we deal with conservation laws. We can consider some other structures and use the same formula if we change the meaning of this differential. Instead of dh, we can consider something else. So in principle, this mechanism works for any cohomologies, for any x invariant cohomologies, roughly speaking. For literally any, maybe we have to be able to restrict them to the equation, to the invariant equation manifold, invariant solutions manifold. Yeah, to epsilon x in this terminology. But one way or another, we can apply this formula to a huge number of situations, to a huge number of symmetry invariant structures, and all of that. So this formula tells us that when it comes to invariant solutions, we have another natural reduction mechanism. One of them is just say that we have some reduction, that is, we have some inclusion of one system of differential equations epsilon x into another system of differential equations epsilon, and using this inclusion we can pull back various geometric structures. But in this case we have another reduction mechanism, and in some sense this reduction mechanism is more interesting because it reduces the horizontal degree of any object in this terminology at least. So formula 23 is the main formula of my talk, and I would say that it's very simple, and you can see that it works for any differential equations, integrable, non-integrable, for symmetries, local symmetries, higher symmetries, contact symmetries, point symmetries, and for a lot of various invariant geometric structures as well, not only for conservation laws. But we consider conservation laws because in this case, it's easy to describe the reduction mechanism in terms of a very simple algorithm and implement this algorithm in REPL and all of that. So we can get essential information about invariant solutions in no time. In this case, we don't have to calculate anything in the case of 1+1 systems and in the case of their conservation laws. Okay, let's discuss invariant reduction itself. So since x vanished on epsilon x, the restriction of the loop derivative to epsilon x is 0, then the fact that the conservation law is invariant, is x invariant, implies that the restriction of this theta to the epsilon x is horizontally closed. In other words, the restriction of the function of this function to an x invariant solution with a connected domain is constant. Because if we restrict this theta to an invariant solution, horizontal differential becomes Ram differential, and we get information that the Ram differential of the corresponding function of the restriction is 0. That is, if this function has a connected domain, then it must be constant, or it's locally it's a constant at least. So function 25 is a constant of x invariant motion in this sense, because if we restrict it to an x invariant solution, we get just a real number. I mean, we don't get just a real number literally, but it becomes a constant. The constant depends on the choice of an invariant solution, and if it doesn't depend on the choice of an invariant solution, then we can say that the result is trivial. So there are trivial results of this reduction, and it's possible to get a trivial constant, the trivial constant of invariant reduction from a non-trivial invariant conservation law, actually. But let me know that if we have another representative of the same conservation law, then formula 26 holds as well. So the loop derivative of another representative becomes the horizontal differential of this combination theta plus loop derivative with respect to x of some function on epsilon. Thus, since the kernel of the horizontal differential is just consists of constants, the conservation law uniquely determines the restriction of this function theta to the equation epsilon x up to an additive real number, but we can say that additive real numbers are just trivial constants of x invariant motion. So this is just how it works for first integrals of ordinary differential equations. Let me note that epsilon x is not an ODE. We still have two independent variables on epsilon x, right? So we don't reduce the number of independent variables. It's not like the reduction in the classical group analysis sense, I would say. The reduction in more or less the same sense, but we don't reduce the number of independent variables in this case. So we don't have an ODE. Epsilon x is not an ODE. That is why the constant of x invariant motion is not a conservation law of epsilon x, because conservation laws of epsilon x are still horizontal one forms, or at least they can be represented by horizontal one forms, not horizontal zero forms. But in this case, the reduction mechanism gives us a horizontal zero form. And this horizontal zero form is an analog of a first integral for ODEs, or first integrals for ODEs. I'm going to demonstrate a bit later. So the reduction mechanism is well defined, at least in this case, in the simplest case, when we consider evolution, a system of evolution equations, 1 plus 1 situation, when we consider 1 plus 1 situation, well defined, and the mechanism works. How can we calculate it? Let's discuss the first algorithm. And the algorithm is also very simple. If we have a representative of a conservation law and symmetry such that the conservation law is x invariant, where x is the corresponding symmetry, then we see that the derivative of this representative boils down to the combination of derivatives of components of the form omega. It's given by formula 27. On the right hand side, we have derivatives of components of the conservation of this representative. Then we see that from our main relation it follows that the derivative with respect to x of p1 must be total derivative with respect to x of our desired function. So basically, our algorithm and our approach is seeking for this function theta, not for its restriction. It is looking for the function theta, but not its restriction to epsilon x. So we need to derive theta itself, not its restriction. And using the horizontal homotopy formula, one obtains theta to an additive function of time of this single variable, and this function can be easily determined from the remaining relation following from formula 27. So minus x of p2 equals to this total derivative with respect to time of the desired function theta. And this relation becomes an ODE of the form where on the right hand side we have a known function. On the left hand side we have just a known function of the single variable t, and on the right hand side we have a known function. That is, it's not a problem to integrate this ODE and to find the corresponding function. So this is how it works. First algorithm, and note that this algorithm determines function theta, and everything here happens on epsilon, not on epsilon x. So epsilon x is not involved in this calculation at all. Hence, the algorithm can be considered global. It doesn't matter whether we have some problems with epsilon x. Say, of course, we imply some regularity conditions, but they are way weaker than, say, the assumption that epsilon x must be an embedded smooth submanifold or immersed smooth submanifold or something like that. So even in the case when epsilon x has some singularities in this sense, some allowed singularities, I would say, we still have no problems with this algorithm because the algorithm doesn't involve epsilon x at all. The only our last step, the restriction to epsilon x involves epsilon x. Our goal is to find this theta, not theta restricted to epsilon x at first. And eventually, of course, we would like to find the restriction. But first of all, we need to find the corresponding theta itself. And this process is related only to the equation manifold itself, to the epsilon. Yes. How can we determine that the conservation law is invariant? It's convenient to use its cosymmetries, conservation laws in this sense. Consider the following system, the system given by formula 31. So we have this variational derivative of the combination. And we require that the variational derivative must vanish on the equation manifold, on epsilon. Here, psi is a vector function given by its components, psi1, etc., psi_m, where components are just functions of the equation epsilon. And solutions of equation 31 are cosymmetries. A non-trivial conservation law defines the following non-zero cosymmetry. So the conservation law defines a non-zero cosymmetry given by formula 32. And the idea is that cosymmetries are not equivalence classes, right? So the inconvenience related to conservation laws is that we have to deal with equivalence classes, but we can deal with something else instead, and cosymmetries are not equivalence classes. So this is the main advantage of the approach related to cosymmetries. We can actually calculate something, do something with conservation laws using them. And a cosymmetry corresponds to a conservation law if and only if the variational derivative vanishes everywhere on GDEs, everywhere on GDEs, not only on the epsilon, on the equation epsilon. The corresponding conservation law arises from relation 34 for some functions P1 and P2, functions on equation epsilon. Maybe it's a bit inconvenient that we mix GDEs and equation manifold here, because on the left-hand side of formula 34, we definitely have something on GDEs. It means that on the right-hand side, we also have something on GDEs, but it's written here that functions are functions on epsilon. But we remember that our algebra of functions on epsilon is a sub-algebra of the algebra of functions on GDEs. So this inclusion is remarkable, but of course, this inclusion only tells us that we deal with evolution equations, roughly speaking, or with equations in an extended Fourier space. In order to describe invariant conservation laws, we need to introduce linearization operator. Let X be a symmetry of epsilon. Let's introduce the operator given by formula 35. This operator maps couple of epsilon to couple of epsilon. That is, it maps characteristics to characteristics of evolutionary vector fields. Yes, and the operator is defined by formula 35, which maps a characteristic to the corresponding derivative of phi. And a conservation law represented by a horizontal form omega is X invariant if and only if for the corresponding cosymmetry one has formula 36. Here we have formally adjoint operator. We have introduced this linearization operator L5, L but this formula involves its formally adjoint operator. This star notation means that we use formally adjoint operator. So in terms of cosymmetries, it's easy to verify whether a conservation law is invariant or not. And we can use them in this way. Besides, we have another algorithm based on the concept of symmetry. In this case, we have proposition 1. If the conservation law represented by a horizontal one form omega is X invariant, then there are functions on epsilon RKI such that formula 37 holds, where theta is the corresponding potential for the derivative of omega, the desired function on epsilon, and psi is the corresponding cosymmetry. So we, on the left-hand side, we have this combination of components of symmetry, of the symmetry and the cosymmetry. But on the right-hand side, we have just total derivative with respect to x. Note that the argument of this total derivative leads to the same concept of invariant motion, in the sense that its restriction to the equation manifold coincides with the restriction of theta itself on the epsilon x, on the system describing invariant solutions. X invariant solution. And if C, phi, and the functions on the right-hand side of the original system don't depend on T explicitly, or just don't depend on T, then theta doesn't depend on T as well. It's easy to see this fact from the right-hand side of formula 37. So if nothing depends on T on the left-hand side, then nothing depends on T on the right-hand side, then we find the corresponding combination, the corresponding argument up to an additive function of T. So, but nothing depends on T. When restricted horizontal differential on the invariant system, nothing depends on T. So this the corresponding potential must not depend on T as well, because of that. Yeah. Let's consider proof of the proposition. The proof is extremely simple. It's based on Noether's identity, which is just an integration by parts. Let omega be a representative of this of the form p1 dx minus p2 dt. Integrating by parts, we find that there are functions rki, such that for any characteristic P, we have formula 39. So in this case, our equation can be considered a family, one parameter family of jets. Roughly speaking, in terms of its intrinsic geometry, it's just one parameter of jets, and we can use this structure. We can consider some formulas when we interpret the family of jets. So formula 39 is written for the Noether identity. Is usually written on jets, but since we deal with evolution equations, we can write formula 39 on the equation manifold. The formula is just integration by parts. We have this left-hand side. We apply our evolutionary vector field to the component P1, and integrating by parts, we get the right-hand side, and that's it. Let us put P equals to phi to the characteristic of the symmetry under consideration. Then from this main formula, it follows that we have relation 40. That is the left-hand side. Since we replace P with phi, our left-hand side becomes x derivative of the function theta. Since these variational derivatives, component P1, are simply components of the corresponding consymmetry, we get relation 41 eventually. And this is the relation that we use in the proposition 1, that arises in proposition 1. So the second algorithm is based on the assumption that nothing depends on T. So our right-hand side doesn't depend on T. The characteristic of the symmetry doesn't depend on T, and the cosymmetry doesn't depend on T. Then we can use the second algorithm. One can find the constant of x invariant motion, applying the horizontal homotopy formula to the expression 42. And the advantages of this algorithm are as follows. The main advantage, of course, is that the algorithm is more tractable in the sense that one can do calculations by hand, because usually cosymmetries look simpler than components of conservation laws. And another advantage is that only cosymmetries of conservation laws are required, but I would say that this advantage is not that important, of course. So it's nice to know that we can calculate by hand, and that's it. In this sense, this second algorithm is not that interesting because it requires something else, or we can avoid of these assumptions, and we can like generalize this algorithm, but eventually this generalization becomes just our first algorithm. So the main advantage is that it can be calculated, something can be calculated by hand, easily calculated by hand, I would say. Let's consider a couple of examples illustrating the reduction mechanism and what we can do with the constants of x invariant motion in principle. I'll consider two examples. Both of them are examples of integrable equations, and they are examples of higher symmetry. But of course, for the algorithm, it's not important. It's not important whether our system is integral or not, whether our symmetry, higher symmetry, or it's just the context symmetry rewritten in the form or not. So let's consider the potential Boussinesq system. The system is given by formula 14. Here we use the following notation. U is just Q1 and V is Q2. Let X be the evolutionary symmetry of this system given by its characteristic. And the characteristic has components 44 and 45. Two components. And the conservation law with the cosymmetry C given by its components, and they're just constants, is X invariant since we have this relation. So we consider only cosymmetries that are constants. So our cosymmetry is a two-parameter family of constants. According to the second algorithm, we consider the corresponding combination on the left-hand side, and it's easy to integrate by parts without any software in this case, and we get formula 46. That is, we get something on the right-hand side, something reasonable, and we know that the result must not involve t, so we can say that the expression under this total x derivative on the right-hand side is the desired function theta, that is, its restriction to the system epsilon x is the constant of x invariant motion. So for each x invariant solution, there are constants C1 and C2, just real numbers, such that formula 47 and formula 48 hold on the solution under consideration. This is how it works. And let's consider another example. Let's consider an example when we can integrate the corresponding system using the constants of x invariant motion. Let's consider the KdV, and let's be the evolutionary symmetry of the KdV given by its characteristic under formula 50. That's 5's order characteristic. And the conservation law, let's consider the conservation law that has the cosymmetry 51. So basically, we consider three conservation laws, right? We have three arbitrary constants here. So we just consider three conservation laws. And the conservation law is X invariant again. So we can apply our algorithms. Let's consider the second algorithm. The second, or the first algorithm. Using it, we get formula 52. And we can eliminate 5's order derivative from the right-hand side of formula 52, because the 5's order derivative appears here, right, in one place. We can eliminate using the constraint given by our additional equation, phi equals to 0, because phi equals to 0 means that we can say that 5's derivative with respect to x is some combination of first order, second order, third order derivatives. So we can eliminate it when restrict this theta to the epsilon x. Eventually, we obtain three functionally independent constants of x invariant motion. So in this case, they are functionally independent. It turned out that they are functionally independent. But generally speaking, I don't know how to guarantee that the resulting constants of x invariant motion are functionally independent. It's more or less reasonable to discuss the situation, predict that they are linearly dependent. But in this case, it's important that they are functionally independent. And I don't know how to guarantee that the resulting constants of x invariant motion are functionally independent. For example, the conservation law with the cosymmetry given by formula 56 is also x invariant. But the corresponding constant of x invariant motion is given by formula 57. And it's easy to see that the resulting constant of x invariant motion in this case is not functionally independent, right? I mean, with respect to constants of x invariant motion 53, 54, and 55, it's just C0 squared over 2. So it is related to the first, to the constant of x invariant motion given by formula 53. They are linearly independent, but they are functionally dependent. And it's a problem in this case. But nevertheless, one can use these constants of x invariant motion together with the shift symmetries. We have translational symmetry here, translation of time and of space. And we can use these constants of x invariant motion and the symmetries to integrate the system for x invariant. Apparently, they are finite gap solutions, and maybe in this case, maybe, I mean, the problem that I don't know the exact relation between finite gap solutions and invariant solutions. Currently, in this case, they are finite gap solutions, or maybe all invariant solutions are finite gap solutions for the KDE. Maybe in this sense, the example is not that. We can use any other examples, of course, but this is one of my questions to the audience. If you can tell me something about the relation, the exact relation between invariant, symmetry invariant solutions and finite gap solutions, at least of integrable systems, it would be nice. But let's finish with this example first. The constant of x invariant motion allow one to express the variables u4x, u3x, and ux as functions of u and uxx, and these constants, arbitrary constants, in a neighborhood of an appropriate point. One of these constants of x invariant motion gives us formula 58, so we can eliminate the third order derivative with respect to x. And eventually, we arrive to the biquadratic equation for ux, equation 59. Its coefficients are given by these functions a, b, and c, and they depend only on u and uxx, right? So we eliminate the derivative except for u and uxx in this case. For example, in the neighborhood of the points u equals to 1, uxx, C0, C1, and C2 are zeros. One can the root of equation 59 given by formula 62. There are some other options, but let's take this solution. It's a real solution. Locally, it works at least. And using the constants of x invariant motion and the equations of our system, one can replace ut ux, utxx, and uxx with their expressions in terms of our variables and constants in formula 63, this partial system or contract system. And then in the neighborhood of the point under consideration, we can rewrite 63 in the equivalent form given by formula 64, and we can express all components on the right-hand side in terms of u, uxx, c0, c1, and c2, using constants of x invariant motion and epsilon x. The a0, a2, b0, b2, the corresponding components of differential forms on the right-hand side of equations 64. We express them as functions of u, x, c0, c1, and c2. And finally, using Green's theorem, we derive the local general solution in its implicit form given by formulas 67 and 68. So this general solution is local, right? Because we have to choose an appropriate point and all of that in this approach. Maybe I think that the solution to this system is well known in its global form, but it's just a demonstration. It's our way to demonstrate how we can use these constants of x invariant motion in principle. Yes, and let me finish with it. Literature on, here we have some literature on reduction methods, our preprint with Alexei Shirikov, and some other papers. It's interesting to know that there is the paper by Anderson et al.'s symmetry reduction operation by complexes. And this paper describes absolutely different reduction mechanism. Their reduction mechanism is essentially based on the flow of a symmetry and on a symmetry invariant representative of a conservation law. But at the same time, their reduction mechanism can do something else, something that our mechanism apparently cannot do in this full chain review. And there is another reduction mechanism introduced by Soyberg and developed in the remaining two papers. And I would say that the reduction mechanism from this talk is just some generalization of the reduction mechanism introduced by Soyberg, but not of the reduction mechanism introduced by Anderson. Yes, and that's it.
Well, thank you. A very nice exposition. Questions, remarks? Well, of course, in such a form, it was not presented, but maybe there, there exist similar works. I'm not sure, but it should be checked. Maybe something inside the UFA school was done, but I am not sure. But I'm doubt. Well, it's better to check, maybe discuss with some people who are in this topic. Maybe Sokolov knows.
Okay, thank you. I'll try to.
But what it's only, well, I'm only trying to be cautious. I do not state that it is known.
Yeah, okay, understand. Thank you.
More questions, more remarks? Okay, thanks a lot. Okay, so we meet in a week, and we shall have a talk by Volodya Rubtsov. Thank you for being here, and
Thank
goodbye. See you next week. Bye-bye.
Thank you. Okay.